Earlier this week, we talked about solving systems of equations with substitution, where we wrote the equations side by side. You took one of them and you solved for a single variable, x or y. You substituted into the other equation and then finished it off. Remember, it was the circle that we drew to be able to finish off our cycle. There's another method of solving these types of equations, and it's called elimination. Either one works. Some people like elimination better than substitution. Sometimes substitution is easier to use because of the type of problem that you're looking at. Sometimes elimination is easier to use. Yes, ma'am.
Sorry about you again, but I need Kirsten Sugar.
Kirsten, she's on her way. Okay, now I'm going to start with something very simple so that you can see the process of elimination. All right, so everybody needs to be eyes on the board. Okay. These are two lines. They each have an x and a y variable. They cross at some point. And so we're going to try to find that point where they cross each other. In substitution, we would have written these equations side by side. In elimination, we're going to line them up one on top of the other. Where if you notice here, your x's are on top of each other. Your y's are on top of each other. Your equal signs are in the same position, and your constants are both on the other side of the equal sign. Do y'all remember what form this is called? Standard form. When you are doing elimination, your equations need to be in standard form. If they're not in standard form already, you can easily put them in standard form. We already worked on that. Now, elimination works like this. It's like a 3-column addition problem where you simply put the columns together. And the goal that you're trying to do is to have one of your variables, either your x's or your y's, where the coefficient is the same number except one's plus and one's minus. Why would that be the goal? Because a positive something minus the same thing is 0, correct? Well, in here, I identify that this is a positive 1y and a negative 1y, which will eliminate the y. Because it's gone. Plus 1 minus 1 is gone. Here, I've got 1x and 1x, which gives me 2x. My equal sign stays in the same position, and I have 10 and 6, which is 16. And so by the y's being eliminated, I've created a new equation with one variable. And it's very simple to solve from here because all I have to do is divide both sides by 2. So when I divide both sides by 2, I get that x is equal to 8. Now, just like with substitution, however, this is an ordered pair. I know one variable, I need to find the other one. How could I do that?
Plug x.
Plug what I just found x to be equal to back into one of my original equations. So if x is 8, I'll plug it into this one. Then 8 plus y equals 10. All right, well, I shouldn't have to do any manipulation with the equation. We should know what that is. What's y? Y is equal to 2. But remember that this is an actual ordered pair, so I need to write it as an ordered pair. It is a point in the first quadrant of our graph where x is 8 and y is 2. That is where those two lines cross each other. God bless you. If you need some tissue, I have some boxes on the back shelf behind Caleb. Caleb, can you give him a box of tissue, please? Thank you. All right, so this is a second process that can be used. Now, this was a very simple problem, and the purpose was to show you exactly what we're looking for and trying to identify. Now, when we've worked with equations before, when we had fractions, I've told you that you can eliminate the fractions by multiplying every part of the equation by the same thing, right? Because what you're doing is you're creating an equivalent equation. where the answer will still be the same, it just looks different. It's in higher terms. Well, suppose we have something like this. When I look at my A variable, I have 4 and 2. That does not eliminate. That gives me 6A. I still have A. I look at my B variable, I have 2 and 2, which is also does not eliminate as it is. So what I need to do is figure out how can I make one of those variables go away. Well, since the B already has the same coefficient, what's the only thing that needs to be done? One of them needs to be made negative, okay? But if I make one term in equation negative, don't I have to change the signs of all the terms in the equation? All right, so all I'm going to do is multiply every part of this bottom equation by a negative 1. And in essence, it's going to change all the signs.
You want to do it to the top equation?
If you can make it happen with only doing something to one equation, if I make them both negative, then now I'll still have a B term because it'll be negative 4 and negative 6A. Okay? All right, so now I draw my line and I do it like a 3-column addition problem because that's exactly what it is. 4 and a negative 2 is a positive 2A. 2B and negative 2B is no more B. The B's have eliminated. Here's my equal sign. I have 15 and negative 7, which gives me 8. And I'm left with a simple equation where I divide both sides by 2 to find that A is equal to 4. Now what do I do? Plug it back into one of the other equations. So if A is 4, I'll plug it back into this one. Then 4 times 4 plus 2B equals 15. That's 16, right?
Right.
So I'm going to subtract 16 from both sides. I have 2B is equal to negative 1. Now what? Divide both sides by 2. So B is equal to negative 1/2. A was 4, B is negative 1/2. Even though these aren't the letters X and Y, they still represent a linear relationship between two things. So it's two lines that are crossing at a point. When I put this in ordered pair form, which letter goes first?
A.
A. A goes first, comes first in the alphabet. So it's 4, negative 1/2. Your answer must be written as an ordered pair. Now James said you don't have to multiply the top equation by something. In this case, no, I didn't need to. I only had to change one equation. But let's look at an example where you may have to change both equations. Okay, if you look at this system, my goal is for the coefficient of either x or y to be the same number. Can I simply multiply 3 by something and make it equal 5? No. Not a whole number. We want to multiply by whole numbers. Can I multiply 2 by something for the y and make it equal 7? No. So in this case, James, I'm going to have to multiply both equations by something. It doesn't have to be the same something. Okay? Each equation can be multiplied by something different. But I'm trying to make one of those coefficients the same. Now, this is how my brain works. Since one needs to be plus and one needs to be minus, and the y's are already plus and minus, I'm going to take these y's and try to turn them into the same number.